Okay, so our next speaker is Dr. Terry Fong, who is Senior Scientist for Autonomous Systems at NASA and Deputy Rover Lead for NASA's 2023 Viper Lunar Rover mission. He is also Chief Roboticist and former Director of the Intelligent Robotics Group at NASA Ames Research Center. Let's please welcome Dr. Fong.
Good morning, everybody. Can you hear me?
Yes.
Great. I'm very pleased to be with you virtually. Unlike Nikki, I'm only here in 2D, so hope you'll bear with me and hope we can actually still have a good discussion and interchange today. I am the Senior Scientist for Autonomous Systems at NASA and the Chief Roboticist at NASA Ames. Today, what I'm going to talk with you about is the work we've been doing within space technology over the past year or so to develop a structured framework and roadmap for space technology research and development, and in particular focusing on our plans for the areas of autonomy and robotics. So to start, can we move to the next slide? I will say that as somebody who spends my day thinking and working with autonomy and robotics, that I'm really thrilled by the fact that there is such a broad cross-cutting interest and demand for new technology in the area of autonomy and robotics for space work. This demand comes from a variety of places. Clearly, there's this incredibly rich and growing drive from the commercial sector to develop space systems. A part of that has to do with the use of robotics for, of course, the lunar surface. And one thing I will say, though, is that a lot of that demand is really crying out for the development of shared infrastructure, which of course is the focus of this afternoon's breakout sessions. Industry clearly needs infrastructure because no one wants to go out there and build their own infrastructure and maintain it, and it's an incredibly high barrier to entry to a lot of companies. And so what's really important is we think about how we can develop infrastructure that can be shared, that is interoperable and can be reused. Secondly, clearly within NASA, there's a tremendous demand from human exploration. As we go beyond Earth orbit and look at the moon and beyond, one of the things that's very obvious to us is that we will still have very limited number of crew out in space. And of course, nobody can do everything. Even just taking care of the spacecraft that they're in demands a lot of support. Today on the space station, of course, we get that support from mission control, which is in almost continuous contact with the space station. We do a lot of monitoring, a lot of just logistics work from the ground. But as crew moves further into space, even on the moon and on places like the Gateway, but certainly beyond that, there's a tremendous demand for things that will support crew, systems that will allow them to be more independent, more autonomous themselves of Earth. And so one of the things that we are very much interested in looking at is how can we use autonomy and robotics to help improve the way that crew can live and work in space. And then, of course, there's science, which for a long time has been the main driver for the use of autonomy and robotics, in particular, robotics in deep space. Science has really driven a lot of very exciting missions. Clearly, you look at the rovers that we've had on Mars to date. They're becoming increasingly capable, carrying greater and greater payloads. But there are missions that are far more demanding than even those that we see today. They're missions that frankly are bolder, more demanding. Missions such as going out to explore, into land and explore Europa, where you're really far from Earth, where you have very little communications, and where frankly the demand for the system to be more capable, more autonomous, is even greater. There are other things too. Clearly we'd like to build very large-scale observatories in space. Some of that can be done with the assistance of humans. But others, especially those observatories which have to be deployed much further from Earth than low Earth orbit, really demands that we be able to do this remotely and autonomously. And all these things together, commercial space, human exploration, science, they demand that we create new technologies, that we mature new technologies, and that we find ways to make these technologies sustainable. So next chart, please. The approach that we are taking right now within the Space Technology Mission Directorate is focused on the following things. First off, it's important for us that we find ways of encouraging and facilitating the growth of the space economy and workforce in this area. It's not sufficient for NASA to do this end-to-end. It's not sufficient to assume that industry can do this end-to-end. We have to find ways to really grow and sustain people who are working on these technologies. Part of that has to do with creating and accelerating a consortium of academia, government, and industry. And the Lunar Surface Innovation Consortium, I think, is a great example of a community that can really pull these different elements together. And as I said, I think a core thing is that we need to find ways to reduce barriers. There's clearly barriers right now to collaboration, barriers to reuse, and even barriers to entry. I know that there are some smaller businesses attending this fall meeting here that really are trying to find out how can you get involved. You may have great technology, but the barrier to entry to space is very high. Space is unforgiving, space is very demanding, and part of the question is how can we use technology to reduce that barrier? So the approach that we're taking in our planning work follows on these principles. First off, we are looking really forward to the future to what we might envision as being the outcome in 15, 20, even 30 years from now. And I'll get to that in a few minutes, talking about 6 primary technology objectives we have for robotics in space. The second is we have tried to be very careful of defining what are the technologies that are needed to build these future space systems. And so we have a taxonomy that describes all the different building blocks that we feel are really important for space robotics. And I really hope that you'll keep these in mind this afternoon when we're talking about things in the breakout sessions. Third, it's very clear that there are a lot of things that NASA can do uniquely. NASA clearly does a lot of work in space, has a lot of unique expertise, has a lot of unique data sets that we collect and manage and curate, and even development test beds right now and test facilities are very unique within NASA. So we really want to leverage that to help all organizations be successful in space. I think a key part of that, of course, is trying to find ways to increase collaboration, especially between the private sector and the federal government here. Part of this has to do with trying to find ways to accelerate the integration of autonomy and robotics into missions, especially that technology which starts out maybe in academia and it's matured or developed into commercial product. And the last bit too is something I think that we all should care about, is how do we really support sustained development of our technology? One of the things that we have been working on right now is trying to find an approach. This is a bit on policy, it's a bit on maybe sort of governance, maybe it's also just in terms of the way that we connect together. But the idea is that we want to find a way to have an open framework for development where the technology development can be done in a modular, interoperable, and reusable manner. So next chart, please. So some of you may be aware that over the past year and a half, the Space Technology Mission Directorate has been developing and using a strategic framework to describe the way that we are approaching technology development. For those of you who are not, there are currently four key areas in terms of how do you get into space? How do you use propulsion technologies to get from Earth to the destination you care about? Second, technologies involving landing. Of course, landing is a very key thing for planetary surfaces. And there's a lot of interesting technologies in terms of perception and terrain relative navigation that are important there. Once you're there, of course, the question is, how do you sustain? How do you live and work there for a long period of time? And the fourth area, which is near and dear to my heart, is, of course, exploration. And one of the core things, as you can see there in red here, is developing advanced robotics and spacecraft autonomy technologies to enable and augment science exploration missions. That's really what I think is important for us to focus on with this area. Next chart. So I mentioned before that we tried to focus our development planning with the idea that we want to move towards an envisioned future. And so we have taken a look at some of the technologies that exist today and given some thought about where they could lead. If we look forward 15, 20 years from now, some of the things that we really care about are the ones that we are shown on this chart here. For robotics, that might mean things such as the capability to have intravehicular robots that can maintain and help support utilization on spacecraft when people are not present. You think about the gateway system that's currently in development. That's a place where humans will only be there a few weeks of the year. So 80, 90% of the time, that will be a spacecraft that is uncrewed. And the question is, how do you maintain that? How do you keep it in a functional state? How do you support science activities that go on when people are not present? A core part of that, we believe, is the use of robotic technology. Robotic technology inside of the spacecraft, not just the kinds of things that we've seen on the space station involving external positioning arms, but really systems that can function routinely inside of the spacecraft. And of course, it doesn't have to just be in space. It could be inside of a habitat, whether that's on the moon or Mars. We are also very interested in the use of new robotic technologies to get to extreme environments to access more difficult places. As Nikki mentioned earlier, and I think Rachel said yesterday too, one of the core focus areas for the Lunar Surface Innovation Consortium is extreme access, and mobility technology is clearly important for that. So some of the techniques that we'd like, some of the technologies we'd like to develop would be those that enable us to explore very long ranges, thousands of kilometers, not just a few kilometers, to access into deep interiors, to handle rock and cryogenic ice, really dangerous slopes, to explore subsurface voids, those kinds of things. The third area in terms of robotics has to do with self-maintainable robotics for heavy-duty surface work. All of NASA's experience to date has been focused on science systems in terms of robotics. You think about the rovers on Mars; those are primary science platforms. What they are not are systems for doing heavy-duty, mining, construction, the really dirty kind of work that robotics is often used for here on Earth. And so the question is, how do we enable those kinds of things? I think this afternoon we'll talk about that as we're talking about how do you deploy and support and maintain infrastructure on the moon. Next chart. So these are just some examples of the kinds of technologies in these areas. I won't go into detail here other than to point out that, for example, if you're looking at intravehicular robotics, the kinds of systems that we're interested in are those such as the Astropy robot system that the space technology developed over the past few years and are now in operation on the space station. Those are free-flying robots that are used for mobile sensor work, monitoring routine interior surveys. Of course, NASA's been doing a lot of development of extreme mobility systems for years, especially at JPL. We have systems such as RoboSimian, which is wheels on legs, basically, or systems like Dual Axle, which is a robot that can split itself in two and connected by a tether to descend really steep cliff faces. We have other systems in development. Razor on the top right there is a system meant for excavation of lunar regolith, and we are currently developing a system for flight demo to do a pilot demonstration of how you would excavate regolith on the moon, as well as we're starting a new project this fall here in the area of modular field serviceable, that is maintainable and self-maintainable robotics for the lunar surface. Next chart. Similar to thinking about the future of robotics technology, we've spent a lot of time thinking about what's needed for increasing the autonomy capabilities of our future mission systems. And so 3 areas that are really important to us are, number one, cooperative multi-spacecraft systems. To date, most of the spacecraft that we have in space operate independently, a single spacecraft. But there are a lot of reasons why having cooperative multi-spacecraft systems, not just in space, where clearly things like multiple CubeSats have been a big area of development, but also on planetary surfaces. We'd like to have multiple rovers working together. We'd like to have rovers and hoppers and landers and satellites all working as a functional team. That gives us the ability to look at activities, to carry out measurements, and to perform actions which cannot be done by a single vehicle. Secondly, it's really important to look at how these systems can be more self-adaptive, fail-active or fail-operational if you prefer, especially for missions that are in very dynamic, unpredictable areas. Thinking about how you might operate a probe that is going to penetrate through many kilometers of ice and explore an interior ocean, such as on Europa, is a good example of why a system needs to be much more capable, much more adaptive, and less planned in advance than current systems. The other thing too, of course, is just like on Earth, where there's been this big push for vehicle autonomy, where vehicles can drive further and faster and longer, we'd like to see how this can be translated into space to increase the reach of our planetary rovers. And so going beyond just driving tens of kilometers over the course of a mission to driving thousands of kilometers, especially very long range over a short period of time. Next chart. Just some examples of this work here. Within space technology, we've been focused on development of a system called Puffers at JPL that's now turned into a future development for a tech demo on the moon in a few years, looking at the use of multiple rovers that can perform a joint measurement together. In space, we have a distributed spacecraft autonomy project that's looking at how multiple small sats can also work together in a very cooperative manner, not just synchronized, but really supporting one another. There's a lot of technology that the Science Mission Directorate has been doing in the area of self-adaptive and fail-active autonomy research. If you're interested in that, I'm happy to talk more with you offline. And I want to point out that in terms of like high progress rate robots, there has been some work primarily in the academic sector, at Carnegie Mellon and also the University of Toronto a few years ago, looking at how these systems could drive further and faster. Next chart. In terms of the technology that's needed for this, as I said, we wanted to make sure to explain to people what we felt are the core building blocks necessary to create these more advanced autonomy and robotic systems. And so what you see here is a taxonomy that covers a lot of different things. I won't go into detail here. If you're interested, happy to share a copy with you. But it covers technologies ranging from self and situational awareness. Everything involves sensing, perception, different kinds of sensors, hazard assessment, anomaly detection, through mobility, which is clearly important for many applications, manipulation, especially if you're trying to interact and work with the world. But then if you go all the way over to the right, it includes things like system engineering and integrity. And I was really happy to hear Kara's presentation before me, where she talked about the need for tools to support this development. I think one of the core takeaways that we have really found is that the development of more advanced autonomy and robotics technology demands different tools. We can't simply rely upon the existing test beds or data sets or even compilers that we might necessarily have today if we want to increase our ability to deploy more advanced autonomy and robotics in space. Next chart. Just some examples of how those technologies can be used to support future things. And I know we will talk more about this afternoon in the breakout sessions. One of the things that's really important, I think, for us to focus on is how do we use these technologies to, for example, perform lunar site preparation. There's clearly a lot we can do with robotics in terms of different kinds of functions, in terms of excavation, transporting materials, building up landing pads, trenching for cables and other infrastructure. All these things require mobility, it requires manipulation, it requires sensing, perception, it requires onboard decision making. Those are the key technologies that we see within the area of autonomy and robotics. Next chart. There's also been clearly a lot of work, in the analysis of how we can build large-scale observatories in space. And I know this is the Lunar Surface Innovation Consortium focused meeting, but just to point out that a lot of the same technologies are useful if you're trying to do, for example, development of an in-space assembled telescope. Back in 2019, there was a large study that was led by JPL as input for the 2020 Astronomy and Astrophysics Decadal Survey. And that study identified a lot of capability needs that involve autonomy and robotics technology, everything from assembly to sensing and verification of the built structure in terms of creating docking interfaces and standardized interfaces. A lot of the core technologies are exactly the same. And I think that's one of the very exciting things about the technologies in autonomy and robotics, that they can be used for many different kinds of missions. Next chart. Just to tell you very briefly here about some of the current investments within space technology. As I mentioned, we have a couple projects, Distributed Spacecraft Autonomy and the Cadre project, which builds upon the Puffer work, that are looking at the use of multiple spacecraft that are function as a team. But there's other work in this area that's very relevant too. We have 2 space tech research institutes that are looking at how these robots and frankly, distributed autonomous systems can support future habitats. We have some early career awards looking at the use of coordinated multi-robots for doing things like self-rescue or mutual anchoring. And all of these things are developed in a way that will help enable these future capabilities, such as systems that can work cooperatively and share loads or be able to better access extreme terrain or deploy large payloads in some mutual way. Next chart. One of the other things that I'm really excited about is this development of the Space Robot Operating System. All of you who work in robotics are familiar with the Robot Operating System, or ROS, which has taken the world by storm over the past decade and become the de facto software that's used in academia and frankly, most industry on Earth. Well, over the past year or so, Blue Origin, working with 3 NASA centers, has been working to find ways of transitioning this software, the standard for robotics development, to use in space. Yesterday, there was a poster that I believe Will Chambers showed about the current work going on, but that's just the starting point. I think it's really important for us to think about how we can transition other similar technologies, things that are used very widely here on Earth towards space, and especially open source software, I think is a key part of that. Next chart. So as I mentioned, we have tried to find a way to really facilitate and support this. One of the things the space technology is looking to do is to develop this open framework, a way to really encourage the reuse, the interoperability, the modularity of this technology. And one way of doing that is to encourage developers, certainly within NASA and those supported by NASA, to create technology and then to make it widely available. It doesn't mean give it all away, it just means to make it possible for people to find out and then reuse this technology. And one thing we're interested in trying to do is develop something kind of like an app store, a registry that allows people to find out what exists, find out how to use something, find out how to interface to these things, and then ultimately use this for their systems. Next chart. In terms of software, as an example, I mentioned Space ROS. Space ROS has been following a lot of work that's been going on over in the Department of Defense. Department of Defense, for example, has a system called ROS-M for ROS military. And that community supports the use, the development and use of this ROS software, but they have a registry that's used to share information. Now, what happens is various developers may release their code as open source, others may release it in some sort of proprietary licensed manner. Others may only want to disclose this, but point out that the software is export controlled, depending on the kinds of technology that's inherent within that software module. We're interested in trying to do something similar for space. And so part of this has to do with looking at how NASA, industry, and even international partners can develop software that is interoperable and release it into some sort of registry where people can then find out about that. Next chart, and I think this is my last chart today. Just want to point out that if you take this approach and apply it not just to software, but to hardware and to, frankly, systems and themselves, there are a lot of opportunities. You can think about how this technology can be more interoperable. There is development, for example, the Lunar terrain vehicle that the NASA is just starting right now. Clearly, it's a great opportunity for focusing on the infusion of interoperable technology. Whether this is at the component level for like a LiDAR or a subsystem level, such as a commercial robot arm. There's also clearly the need for us to be able to look at how NASA can better release the technology that we are developing to support industry. And along those lines, I've been talking with some of our current projects, such as the Cadre demo, and looking at how various bits of their software stack can be released to industry. And at the end of the day, what I think I really like to leave you with is this message that in order for us to really turbocharge, in some sense, the way that we develop and deploy and use these systems on the moon and beyond really relies upon this idea that we're able to make the technology reusable, modular, interoperable, so that people are not just constantly reinventing the wheel over and over again. It's really a core message that I think underlies what we're trying to do for technology planning, especially in the area of autonomy and robotics within NASA. And I hope that you all join me in making that a reality. I'll stop there, and I think we have a few minutes for questions.
Thank you, Dr. Fong. Yeah, we have plenty of questions for you, actually. So let's see if we can get some time to ask them. So the first one, do you expect NASA will begin to require survive the night capabilities for its autonomous missions? And if so, at what point do you suspect that might be implemented?
Yeah, absolutely. I mean, I think one of the fascinating, challenging, and highly problematic things about the moon really is the lunar environment. The fact that we go from relatively warm daylight conditions, especially in the equatorial regions, to areas of extreme darkness, extreme cold, means that if we want systems that can do things more than just a few days at a time, perhaps more than just 2 weeks at a time, we have to be able to survive the night. Of course, there are lots of different ways to do that. The systems don't have to do it themselves. I think shared infrastructure, things that allow a system that maybe not able to survive by itself, but can rely upon something else for power or heat, is very important. I certainly hope that there is some thought about how to create that kind of infrastructure this afternoon.
Great. So what bottlenecks do you foresee? You mentioned the lunar surface. Is there anything technological that you anticipate?
Well, we look at low Earth orbit, or we look at Mars, and we think about, why our systems so successful there? What enables those? And it clearly has to do with the fact that there is infrastructure. There's communications infrastructure. You look at Mars, one of the great things we have is the fact that, NASA and some of our international partners have developed a series of orbiters that provide communication relay services from Mars. That enables missions to depend upon that. They don't, not every mission has to deploy their own comm satellite. Clearly, we need to be able to make use of things like that for the moon. And I would contend that, we have an opportunity on the moon as well, not just in terms of things like comm, but other services. The fact that we are so close to Earth means that we can really offload some things, such as processing from onboard spacecraft to processing on the Earth. Just like we rely upon cloud computing for a lot of our daily life here, we can also offload some of the software and the processing from lunar systems to the Earth. As an example, the Viper mission, which I know that Dan Andrews is speaking a little bit later today, that mission has chosen to take the flight software that normally resides all on board the robot and split it in two. So some portion of the flight software isn't actually in flight. It's actually running on the ground and connected via communications between the moon and Earth.
Great, thank you. What infrastructure can NASA rely on external partners to provide to enable autonomous robotics on the moon? Some of them, it sounds like you may have mentioned right there, but are there others?
Yeah, so I mean, obviously beyond communications, there's a need for positioning systems. A lot of things on Earth have really been enabled by the creation of the global positioning system and similar things. Finding ways to create that kind of positioning infrastructure for the moon, either globally or within targeted areas, is very important. I think trying to think about how do we support infrastructure for maintaining these systems. Like I was saying earlier, to date, at least for NASA, the systems we've built have typically been one-off, systems that are designed to last a certain lifetime. We don't have a way to actually repair them. But if you think about the overall infrastructure and even the supply chain needed to support that, how's that going to work? Do we have the service station on the moon for robots? I have no idea what that's going to look like. Maybe be purely robotic, but how do you supply that? How do you get a part, from Earth to the moon? Do you make it in place? I think those are really interesting challenges that we need to take a look at.
Great. So we still have a bunch of great questions here. Let's see if we can ask one or two more. Is there anything being done for applying autonomous systems for growing plants for food on the moon? And this one's unique because it's by somebody other than anonymous. This is Ms. Carol Stoker. Thank you for asking the question.
Okay, so hi, Carol. We haven't seen each other or talked to each other for a while. I will admit that that's outside my area of expertise. I do know that there has been some work within NASA, particularly at the Kennedy Space Center, looking at ways to grow plants in space. And obviously, there's a lot of motivation for that, especially as we get beyond Earth, and nobody wants to live on just packaged foods all the time. It is a really challenging thing because even on Earth, the use of robots for supporting the growth of plants is a really still early area. There's success clearly in agriculture, large scale agriculture. I mean, we have external harvesters, but if you're talking about like growing individual plants, or especially things indoors, I mean, that's still very much early days for robotics.
And I think we'll ask one more question because it kind of comes down to this in many ways. What is the funding outlook for the Tippy Point program in FY22, and how many that may impact NASA's autonomy development timeline?
I think that yeah, well, so I think Jim Reuter mentioned that briefly yesterday. I don't myself have the details about really the budget profile for the next tipping point call. Jim did mention yesterday that they were looking to gather some information, and that's really, I think, focused in terms of demand and also interest in terms of particular areas. I would say that if people have ideas about what NASA should focus on in terms of autonomy or robotics technology, we'd certainly love to hear from them. And I think it's part of the reason why we have meetings like the one that we're having this week. The things that I did talk about are things that we ourselves believe are important, and is a collection of input that we've gotten from industry and from science and from human spaceflight. But it's not meant to be a fixed thing. We're looking to gather more input all the time. No plan is perfect. No plan, lasts forever. And so if you have thoughts, suggestions, ideas, by all means, reach out. We very much want to hear them from you.
What? Oh, we have Nikki would like to add something.
Great.
That's a good opportunity to kind of reiterate some things that Jim said yesterday, because I think this will be really important to this group. So what we're working on releasing, we affectionately call them the 10 pagers, but we've been collecting our key priorities and gaps for each of these capability areas, including all the things that Terry just talked about from a NASA perspective. Those will be coming out. Jim mentioned the RFIs yesterday. Those will be coming out for each of these. There's 10 areas total, I think, out to industry, general public, universities, nonprofits, everyone. APL also in the focus groups will be talking about those for each capability area. When those go out, we'll make sure to blast it everywhere, LSIC newsletters, everything, because we really, really, really want the feedback. The idea there is to put the RFIs out first so it can help influence the tipping point topics and solicitations. And like I said yesterday, making sure that we are honing in on where it makes sense, right, to leverage you guys, right? And then what are the areas that NASA needs to be doing more of and investing more in from kind of a pipes and roads infrastructure perspective to enable all of you better. So that's going to be really key, and those should be coming out late calendar year, early next year is what we're shooting for. We're hoping. So fingers crossed. But a lot of the priorities and gaps talked about in the focus groups through LSIC relate heavily to those. So that's why I really encourage you guys to participate in those as well.
Thank you. Let's thank Dr. Fong one more time. And